All right, here we go again. So some of these things I had trouble with at first. Hopefully you're just doing this for extra practice and not struggling the way I was. If you are struggling, that's okay. You'll be hopefully this will help you understand it better. But this is dealing with epoxide reactions, and these everyone loves epoxides, right? So um let's start with A. So when I first see A, I see that this hydrocyanic acid. So clearly this is one of those acid catalyzed, what's it called? Epoxide ring opening, right? Reactions. So what's going to happen here is CN, this super weak acid, is somehow going to get deprotonated to form the cyanide ion. And you get this, and this does say just draw the major products and not the mechanisms, but I'm going to go through for the first couple ones at least. I'll go through the mechanisms so that way we can understand why that's the product. Okay, so for this one you get something like this. All right, and the thing about these is that sometimes we forget, okay, now we have this product for this first reaction or for this first step. Now, which carbon is the cyanide gonna attack is the question. And our textbook at one point says that strong nucleophiles like cyanide will attack the less sterically hindered one. That is true. However, when you have this acid catalyzed epoxide, I'm not sure if that's the correct terminology, but when you have an acid and you're doing epoxide reactions, you end up with a positive charge on the epoxide. So what do we know about oxygen? Oxygen does not want to have a positive charge. So oxygen is actually, we can kind of think of it as being angry that it has a positive charge. And it's actually going to want to do something. It's going to want to withdraw electrons from one of the carbons. So that way it's less positive or less positive in this state. So that way it's lower in energy. And if it's lower in energy, this reaction can occur faster, right? If things are lower in energy. Okay. So does it make sense? Or let's see, which carbon would it want to remove electron density from? If we remove electron density from the carbon on the right, we would have a partial positive charge here. Versus if we removed electron density from the carbon on the left, this one here, we would have a partial positive charge here. Now the question is, which one would be lower in energy? We already know that if we're talking about partial positive charge on carbons, we kind of have an idea of which carbons, when it comes to having a positive charge, are more stable. We know, and aside from benzylic and allylic carbocations, we know tertiary carbocations, something that looks like this, is more stable than secondary, which is more stable than primary carbocation. So something like this, right? So let me write primary. So therefore, the one that's going to be lower in energy is the one that's more substituted. That means the carbon on the left is more substituted, or it is more substituted. That means it's more stable, right? The one that's more stable is going to undergo a backside attack from this cyanide anion. And again, that's only because in this case, we have this positive charge on the oxygen. It's going to want to withdraw electron density from one of the carbons to make it less positive, right? And it's going to want to do that it's going to want to withdraw the electron density from the carbon that is able to withstand loss of electron density. And the one that's able to withstand the loss of electron density is the one that has the added support of extra hyperconjugation and inductive effects from other other carbons that are connected to it, right? Therefore, if I erase all this stuff, this cyanide is going to attack the more substituted one because that's the more positively charged one. And the more positively charged one is open to incoming electron density, right? Because this cyanide's bringing electrons with it. So it's more likely to, the negative charge here is more likely to attack the partial positively charged carbon right here, okay? So we see this happen, and then we get a product that looks like this, and that is going to go up there. So you get something like that. And it would be a backside attack, so I'll draw that differently. So OH there. And then something like that here. Yeah, let's do like that. CN. All right. So for this next one, similarly, it is a acid, it has an acid, and you see an epoxide, right? So we know what's going to happen here. We have been through this same exact thing that's going to happen. This is going to take those electrons, and then we end up with this intermediate here where you get that there and that there. This has a positive charge. We know that the fluoride anion is going to want to attack the carbon that is more positive. The one that's more positive is going to be the one that's more substituted, right? Because it's lower, that would be lower in energy than having the carbon that is less substituted be the one that's more positive. So in this case, the one that's more positively charged is this carbon here because it's more substituted, okay? So it has this partial positive charge there. That's going to attack it from the backside. You're going to end up with something like this. Right? That's your product. Now we have methoxide. That's an interesting. When you have, in the presence of a strong nucleophile with no acid, it's always going to attack the less sterically hindered one. And I'm not, I mean, it makes sense, right? Because in order for it to go in a SN2 like, or it's going to go in an SN2 mechanism, it's going to want to attack the one that's less sterically hindered. These are the ones that are a little tricky, right? Because it actually, while it's SN2, it's going to the more substituted one. And again, that has to deal when we have a positive charge on this oxygen. But in this case, all we have here is methoxide that has a negative charge there. And this is a strong nucleophile already. So it's already happy to go SN2. This is a technically kind of a good leaving group because of the angle strain. So this can go in here, doing that, and you would get this here. So you do the O minus. There we go. And then now we treat it with some acid. Sometimes you can see it done as water, mostly some sort of acid that'll go ahead and protonate that to form this. So that. There. That's your problem. Yeah. So here we go again. We have a acid, right, and an epoxide. The only thing an acid can do is protonate, so we're going to protonate the epoxide. And you're going to end up with this intermediate. And this one right here, plus charge there. Now we have our Br minus. And again, the one which carbon is going to have a partial positive charge? Because that's the carbon that's going to be open to And we're only looking for these on the ones that we have this protonated alcohol or this oxygen giving it a plus charge. So the one that's going to have a positive charge is going to be the more substituted one because it's able to withstand a partial positive charge better because of the hyperconjugation and inductive effect, right? So here we go, be that one there. The one that has a partial positive charge is also going to be more open to an attack by a strong nucleophile, right? Because um, it's bringing electron density to this partially positively charged carbon. So there we go, it's going to do that. If that happens, that's going to happen too. I need to start explaining this because it's in my head, I just say that happens, but y'all need it. So what I mean by this is this bromine is going to attack this carbon here because it's more partially positive than this one. And that's going to cause this bond to break right here. Those electrons are going to go to the oxygen. And then you're going to end up with this. So, ooh, okay. Dun, dun, dun. Okay, and that works out. Okay, we're in the home stretch now. And here in E, we have some stereochemistry involved. So sulfide, what do we know about SH minus? It's a strong nucleophile weak base, right? So with that, we know that strong nucleophiles always attack the less sterically hindered carbon of the epoxide ring. So in that case, sulfide's going to run in here, attack this carbon from the back. So these electrons are going to go into that. If you draw a bond to that carbon, you got to break a bond, right? So that's going to go ahead and pop off onto the oxygen, giving you this intermediate here. We have this extremely strained ring to begin with. That's crazy. You have this cyclobutane ring, which is extremely strained, angle strained. And then you have another one. That's an interesting problem here. Anyways, we know that this is going to occur through a backside SN2 attack, right? So you're going to have inversion of stereochemistry there. So SH is going to hit it from the back. And this is going to be on a wedge. And this is going to be on a dash there. There's no change there because none of these bonds here are breaking. Okay, so these stay the same. And now you pronate that to form your final product. Okay, so I know I'm gonna go ahead and just go ahead. Sorry, I'm gonna go ahead and just go. I was about to say go ahead and go ahead again. That's so weird. Okay, I am going to go ahead and just give you the answers for the rest of them and not the mechanisms, okay? Because I think we've already done enough of these mechanisms to see to understand the basis of this stuff, right? So for F, you have an acid here, and then it's going to go to the one that's less sterically or more sterically hindered. So you're going to get this. So that Cl CH3, and then you end up with that here still. Okay. And for G, it's a strong nucleophile, so that's going to go to the one that is less sterically hindered. So that would go to this one here. So backside attack, OH, you have Cl. From here, we are going to have an acid catalyzed one again, right? So we're going to attack. We know that the chlorine or the chloride is going to attack the one that's more sterically hindered in this case. So you're actually going to end up with something like this. Backside attack on that carbon on the left here is going to result in inversion of stereochemistry. So CH3 on the wedge now, and your Cl on the dash, and then your OH here. Okay. And then lastly, for I, it would be a strong, it's going to go to the one that is less sterically hindered. So that would be the one here on the right. So strong nucleophile attacking the one that is less sterically hindered. So you get this, oops. That's going to retain there. You're going to get OH. No inversion of stereochemistry on that side since no bonds are broken. But you will hit this carbon through a backside attack on the CN there. And that would be your product. Okay, so I don't have any more. All these are done, and I'll probably finish the rest soon. But yeah, okay. Thank you for watching this video, and I'll see you next time. I hope this video helped. Thank you. Bye-bye.